I want to give you an overview of sine tropical convexity. This is based on joint work with Laci-Weg. So this is based on 2 papers, one with Laci-Weg and one with Mateusz Skomra. So I want to give you an overview of different versions of sine tropical convexity. And for this, so the agenda is essentially, I want to convince you that the tropical convexity, which you might know or you might be more familiar with, is actually just a very restricted version in a tropical non-negative orthant, and one should actually study sine tropical convexity more. We actually exhibited 2 well-behaved natural notions of sine tropical convexity, which we named TO convexity and TC convexity. They are natural in the sense that they have several beneficial properties, and we can give several equivalent characterizations of them. And along the way, hemispaces or like TC hemispaces will come up as a tool. And in general, well, convexity is a lot about separation, and so this will come up as a tool along the way. And 2 motivations for us are signed tropical linear programs, or originally tropical linear programming, but so now let's say more generally signed tropical linear programming and real Bergman fans. And just to go back a bit in the history, so tropical convexity, I mean, I assume familiarity with tropical geometry at this workshop, but maybe let's go a bit more in the direction of tropical convexity. Well, it's like tropical geometry, a limit version of convexity, and so it was also called extremal convexity, and it was made very popular by a paper by Devlin and Sturmfeld, where they showed some duality to regular subdivisions of products of simplices. And it actually has quite a lot of modeling power and optimization. So I would also, the talk which we've just seen, I would say this also falls into this direction. And then there's the quite a fruitful direction on tropical linear programming, because due to its connection with classical linear programming. So there has been quite a few very nice contributions by Alamijon, Moshimol, Gobert, and Josvik, and actually also follow-up work by subsets and supersets of the authors. And another motivation comes from the equivalence of tropical linear programming with mean payoff games, because this has an interesting complexity status. So just this was as a warm-up and to get an overview. And now I want to motivate sine tropical convexity, because I think this is actually an even more natural framework for several phenomena in tropical geometry, or let's say tropical convexity, but also more generally. So just to set the scene, I'm mainly talking about max plus tropical geometry, and I will use these symbols for the sum and product being maximization and addition. And yes, we are, I guess, all quite familiar with that. And just maybe to point out, so again, this weird behavior of equations, which we see here, and already this is a bit unusual, right, for people who would not know tropical geometry, but it will become even weirder if we go to the sine tropical setting. Well, this we all might know the slogan that we replace sum by max and product by sum, and that this actually corresponds to maybe some asymptotic idea, but inherently this really forgets signs, right? So to do some signed tropical things, we have to really break some of these ideas. Yes, just also as a reminder or warm up, the usual tropical convexity can be seen in the following way. So we take these combinations of vectors of a, like say, columns of a matrix. And so the idea is that we take non-negative combinations such that the scalars sum up to the tropical 1. And then we get these nice pictures by taking these combinations. And so for me now, this is actually really a picture in the tropically non-negative orthant. So let's say here is the point minus infinity minus infinity. So for me, this is the tropical non-negative orthant. And so it's actually getting more interesting if we look at these combinations, if we go between these orthants, let's say. Yes, and in particular, why does this work so nicely? Well, a priori there's no cancellation, but this will be really the problem for us, that there is just no cancellation inherently in tropical convexity in these combinations. But if we want to go between orthants, then we have to model this in some way. And also just to look at the application, which I also already mentioned, tropical linear programming means to find a solution of a tropical linear inequality system of this form. And so we're looking for a solution in R to the D, or maybe tropical numbers to the D. And this has an intriguing complexity question. Complexity status, namely it's in NP intersected co-NP, and there's no polynomial time algorithm known. So there's really also an interesting algorithmic question in the background. And so this has been widely studied, and related problems have been widely studied in theoretical computer science and related areas. And there's this important subclass of parity games, which has seen recent breakthroughs. And so this also has explicit applications in machine verification and so on. So while in this talk I will present mainly, let's say, new geometric insights on these objects, so I have a clear motivation also from these algorithmic questions. Yeah, so let's go to a more geometric point of view. Again, tropical convexity as a limit of classical convexity. Explicitly, it would be like a logarithmic limit. And this allows to transfer results about polyhedra in the non-negative orthant, so this is crucial, to tropical polyhedra and vice versa. And so this was also behind some of these new insights about classical linear programming, which I just briefly mentioned before. But actually now if we look at the geometry itself, so tropical hyperplanes or tropical half spaces do not really, like the tropical half spaces, which are usually considered as tropical half spaces, do not really behave like half spaces or hyperplanes in R to the D. So for example, if we look at this configuration in the plane, then let's say we have these 3 tropical hyperplanes. And by the way, maybe you think of tropical hyperplane as this. This is, let's say, the more tropical geometry point of view, while let's say the more tropical convexity point of view is that we really, a hyperplane should be the boundary of a half space, and the half space has some additional sign information. So really this would be a tropical hyperplane, and this and this. Yes, but okay, so in the plane, this means we have actually 3 lines, but these 3 lines are really generic in some sense, but they do not intersect, and that's not very desirable, right? And this is also where the sign tropical convexity comes in. So we really want to extend to the other orthants, and I did not tell you now how we did this or how one can do this. So maybe if you have seen patchworking, then you can think of, well, one can just do some patchworking and then one gets exactly this configuration here. But I will show you a framework motivated by like convexity, which will also give this. Yes, so now we extended these 3 lines to all 4 orthants, and now they really intersect in 3 points as expected. Okay, so that was the basics and some motivation. Do you have any questions so far?
Could you repeat how to see these the tropical hyperplanes are not don't look like the lines? The what you said in the previous slide. Yeah, could you repeat that, please?
So the difference between this and this?
Yes, exactly.
So this is kind of the vanishing idea of tropical convexity, of tropical geometry, that we require that the maximum is obtained twice, right? So I give you a tropical linear form, and I require that the maximum is obtained twice, and then I get this shape, right? That's, I guess, what might be used to. But then actually, let's go. Yeah, it's fine. So let's look at this system here. Okay, this is clearly some version of a tropical linear inequality system. Okay, and so a tropical linear inequality describes a tropical half space, so a shape of this form. Maybe let's, yeah, a shape of this form. And so a different interpretation of hyperplane is, well, I want to be the boundary of a half space. So, and if I take this as a definition, then I get these other shapes. Does it make sense?
Yes, thanks.
Okay.
Can I also ask a question? But I think you already answered mine. So if you just go to the next slide, you have like these, I mean, like the blue one looks like part of a tropical max line, but the red part looks like a tropical min line, part of a tropical min line. And is it the same reason that you have like 2 sides of the inequality? So I mean, the red line, right? It goes in direction -1 + 1, like at its edge, and that's technically not allowed if you fix in the max convention.
But if I only restrict now to this positive orthant, right, then they are clearly 3 max thingies.
Yes.
And I think the fact that it might look also like a min thing really comes from the fact that this is due to a reflection, and this reflection is really just because I go to the other orthants. I think that's not so much about.
So I guess next symmetrization will be presented some kind of way of introducing minus.
Exactly. So that will be the next slide. So that's why, I mean, now we have the setting. We are intrigued about tropical convexity, and now let's do some symmetrization. Okay. Yes. Namely, as I said, we want to model something like negative numbers and cancellation. And maybe let me also put an idea up here, which will come up in a bit. But so as a reminder for me also to mention it, or that you can already ask a question. So okay, let's say so my approach here to model this is via the symmetrized tropical semiring, which goes back to 1990 or even earlier. We use you just use this reference for now, and yeah. So the idea is that we have, let's say, the tropical numbers, and then we add a negative copy. So like really similarly to we take the natural numbers and add a negative copy to get the integers. But actually, if we now want to do computations, then we actually cannot have proper cancellation. That's why we need to have a blown up version of a 0. And let me show you. Okay, so now the remark is about hyperfields. Well, this blown up version of a 0 can also is also captured in the formalism of hyperfields, and I will actually use this in a bit. Yes, I'm not sure what your background is. So this is a different version of looking at the signed tropical hyperfield, actually. Yes, and so, but I want to work with these balanced numbers, They are called balanced numbers. And so the idea is, okay, so usual max sum is okay, max of 4 and 4 is 4. But as soon as we would get cancellation, we get such a balanced number. And otherwise, again, the let's say absolute value wins. So in the absolute value, we again take max. So we take the max of 4 and 5. 5 wins, but we take the sign of the 5, which is minus. Again, so if we add an already balanced number, then we get a balanced number. So 0, like these blown up zeros absorb everything. Sorry, absorb everything. And for multiplication, we get the usual rule. So this is kind of plus times minus equals minus. And we do the usual multiplication, tropical multiplication being the same as sum on the absolute value. And again, do not get confused. You can also have still the usual negative numbers, but with such a weird sign in front, which is now like the signs are plus, minus, and balance. Okay. So don't worry if you did not get much into this formalism. I wanted to present it, but I will try to mainly talk about geometric objects, where the explicit formalism is not needed. Are there questions nevertheless? Okay. Yes, so I just tried to introduce this formalism, but as I said, we will mainly talk about geometric objects. But for this, we kind of need some of this terminology. Well, so what is a hyperplane? A hyperplane is the vanishing locus of a linear form. So yes, here we have a linear form, and now but vanishing is just not like 0, but this blown up version of 0. Again, so a half space arises by taking a linear form and looking if it's positive or negative or non-negative. And again, so this would correspond to positive, and this is positive or 0. And again, 0 is this blown up version of 0. And so we get hyperplanes, open and closed half spaces as subsets of these signed numbers. And really, you can think of these signed numbers as just we have all the orthons we should have. Okay. Now with this terminology, I want to reformulate these max plus systems. So recall before I had a system of this form, and actually often people write it like this. Well, but usually, classically, I would like to have something like classically a linear inequality system should look like this, right? Or equivalently. Okay, and now this condition of being non-negative is really being replaced here by being either positive or balanced. And yes, so these systems I described before in this terminology can be written like this. And now really this part here is actually a positivity condition. And with this positivity condition, we have that the problem is an NP intersected co-NP. That's what I've shown you before. But actually, so what happens if we drop this? So I mean, classically, one would say that this is equivalent. But here in this setting, suddenly we get an NP complete problem, and maybe you say, oh, it's not so surprising. It's somehow very general. But what I really like about it is actually a quantitative version of the SAT problem in the following sense. So if we have formulas where we have only the coefficients 0 or minus 0, 0 or minus 0, then this is actually the same as a SAT formula. So having more general coefficients in this sense, really a quantitative generalization of SAT formulas. Okay, so far about this motivation in this direction. Yes, now with this formalism, let's try to define convexity. Yes, I don't want to have balanced numbers in my convexity. This is mainly only to model 0, because my convexity should only live in these signed numbers. That's why the multi-valued addition comes in, which is usually here multi-valued addition, which now then forms the hyperfield with these other operations, the sign tropical hyperfield or real tropical hyperfield. If we use this operation, which really just replaces this balanced A by this interval, so this is really the idea, then we can essentially just use the usual formulation of convexity by non-negative linear combinations, non-negative, such that the scalars sum up to 1. Yes, and let me point you to a very recent paper by, very recent paper by Ben and James. And I saw James in the audience, maybe he's still here. I think we haven't met. I haven't seen Ben, but I really like that work. And so, so this idea really also extends to other hyperfields to some extent. And yeah, I'm intrigued to see more about this. Okay, so this is one version. I will explain why this TO comes in. Where the name TO comes from, I mean, sorry. But this is a natural way of constructing convex sets, right? With these signed numbers. Again, so the idea was, okay, we want to take, let's say, usual convex combinations. Then maybe we get this weird cancellation, and there's a natural way to resolve them. This natural cancellation. Okay. So let's look at the arising geometric objects. What happens here? So if you have generic points, then actually it looks a lot like the tropical line segments in one orthants, just extended in a very natural way. So also tropical line segments in one orthant are already the union of ordinary segments. And really in the generic case, this multi-valued thing only happens at most once per coordinate, so at the same time. So these two sets really correspond to this in this part here. Okay. So this is a generic case. So this looks like, okay, this is the right notion of convexity. But actually in the non-generic case, when suddenly the cancellation can happen in two coordinates at once, then we get then these balanced entries really blow up a thing. So, and then suddenly we get a two-dimensional object in this case, which is, I think, surprising or weird. I'm not sure how to say, but well, we are surprised, I would say, what happens here. And then one gets doubts, is this really the right notion? Yeah, but it actually is. In particular, because one gets also an exterior description of these things, namely open tropical half spaces are actually TO convex in this sense. And So the outer description is, if we have the TO convex hull of finitely many points, then this is actually the intersection of all the open tropical half spaces that contain these points. So really this hull operator is also has this outer description, as one might like. But actually, okay, and now we are so we need open tropical half spaces. That's why TO tropically open. So that's how we coined this name. So in the first paper with Lazzi, we called this just generally signed tropically convex, but then we realized in the follow-up work with Mateusz that there's actually another notion which arises naturally, because you might already ask, but what about closed tropical half spaces? Not sure if you ask it. Do you have any questions about that?
I actually have a question. Do you hear me?
Mm-hmm.
Yeah, okay. So when you go from one orphan to the other, so is one orphan like all the tropical numbers from -infinity to +infinity? So are the axes like
Yes.
do they have the coordinates -infinity?
Yes, yes. So this is here is really the point, -infinity. That's the origin.
Okay, so to have like a visual representation, you need like a logarithmic scale.
That's why I do not put numbers there.
Okay.
That's why I only have these sketches indeed.
Thank you.
Thanks for the question. Very reasonable question. Okay, yeah. So here it turns out open tropical half spaces are the right thing to look at, and even worse, actually, as I said. I mean, what about closed tropical half spaces? Even worse, it turns out closed tropical half spaces are actually not TO convex. So that the interior is TO convex because it's an open tropical half space, but the closed half space itself is not TO convex. And so really one can see this easily from the picture we have seen before. If you look at these 2 points, then actually if we take their TO convex hull, there should be this object here, or maybe this, sorry. Like there should be some 2-dimensional object in between, but it isn't. So this closed half space is not TO convex, which let me go briefly back, is also interesting in this framework here, because all these, so this is actually an intersection of closed tropical half spaces. So the feasible set is an intersection of these signed closed tropical half spaces. So really the fact that these TC convex, that these half spaces are not TO convex is kind of reflected in the fact that we get an NP complete problem. So there's really something interesting going on in the interplay between the geometry and the algorithmic problems. Yes, so but actually closed half spaces are a very natural object when we want to think about separation. And I want to also motivate this from the Puiseux point of view or evaluation point of view. We already were talking about tropicalization of varieties today. So I just thought I put one slide about Puiseux series and sign valuation. So again, Puiseux series, I don't want to think too much about which version of Puiseux series to take. Let's for now take, let's say, something like generalized real Puiseux series. I want it to be real, so because I want to have an order, and so the order is given by the leading coefficient. So if that is a non-negative, then my real Puiseux series is non-negative, and so on. Now I want to extend the valuation, which is used for tropicalizing it, to a signed valuation, which really takes into account what is the sign of the leading coefficient, and so really we look at this. We look at the sign of the leading coefficient, and the valuation really gets. So this is again we take the exponent, but the sign of this thing is now the sign of the leading coefficient of this series. So the sign valuation, and as always, the extended component wise to vectors, and then element wise to sets. Okay, so and this is what is used for sign tropicalization. And now let's apply this to closed half spaces. Okay. So on a closed half space now over the generalized real Pessoa series is just again a set. I take a linear form. I look if it's non-negative, and well, now if we take the signed valuation of this object, we really actually get. So we're talking about closed half spaces. So then we really get a closed tropical, signed closed tropical half space, where we just take the valuation of this coefficient vector, the signed valuation. So these closed half spaces arise very naturally. In particular, as I said, I mean, as you know, from using tropical geometry, working with tropical geometry, it's always interesting to see what happens. They are up there and over Pessoa series, and then down there in the tropical world. And so over Pessoa series, also the closed half spaces would be the natural object used for separation, and again, separation and convexity play well together. And actually, in particular, the separation result which one has over these Pessoa series also gives rise to already a separation result, just stated here, or then the let's say geometric implication stated here. So if we have a closed convex semi-algebraic set X, then its signed valuation is actually the intersection of the closed tropical half spaces containing it. So this really comes essentially from this. Okay. Also maybe should be more like a implication in this direction. So here we really get an outer description of these sets. Again, we take a closed convex semi-algebraic set over Pessoa series, take its signed valuation, then we get an outer description of such a set by closed tropical half spaces. Remember before, for TO convex sets, we only get a exterior description by open half spaces. So let's look at a convexity which is given by these closed half spaces, which then we coined to TC because of tropically closed. We look at tropically closed half spaces. But this is several subtleties. That's why we start with, we take the convex hull of 2 points first. So which is essentially like a line segment. And now we just want a TC line segment to be the intersection of all closed half spaces which contain 2 points. Okay. And from this we extend to arbitrary sets. We want a set to be TC convex if it contains these TC line segments for all points in the set. And actually then this fulfills other nice properties of convexities, so that it's given essentially by the polytopes. So the convex sets of convex hulls of finite sets, but also this classical property that the hull operator is given by taking the intersection over all convex sets containing the set. Okay, so we defined this Hull operator of TC convexity from line segments, but for these line segments, we used the idea that we want to take the intersection of all closed half spaces containing let's say the endpoints. Yes, again, so let's look at what we get as geometric objects. Generically, and this is again an indicator that this is kind of a right notion, I would say. So generically, these TC segments coincide with the TO segments because yes, so we cross the Orsons at most once, so we don't get anything here, but now for the non-generic situation, we do not get this blown up part, but something on the contrary happens. This just vanishes. So we really only get this set as TC convex hull in the non-generic case. So in particular, and this is actually quite undesirable in general, the TC convex set may be disconnected. So this was quite disappointing, but still this TC convexity has so many desirable properties that we still think that it's a right notion. Really, that the TO convexity and TC convexity both help to describe the phenomena in the, let's say, sign tropical world correctly. Are there questions?
I think you can proceed.
Mm-hmm. Yeah, I just also needed to drink. Thanks. Yes, so let's look at a few properties. And so indeed, so this TC convexity fulfills many nice properties, I would say. So essentially, by definition, it's closed by intersection nested union. Then really the half spaces now are all TC convex. All the versions of half spaces and hyperplanes are TC convex. Again, also essentially by definition, intervals are TC, like TC convex intervals are TC convex. Then the connection to TO convex sets is also quite nice. On one hand, the TC convex hull of a set is contained in the TO convex hull. Only this vanishing of these big chunks can happen essentially. And in particular, each TO convex set is also TC convex. So really all the statements we can prove about TC convex sets also hold for TO convex sets. And then on the topological level, while, as we said, TO open half spaces are TO convex, so their closure, which is a TC convex space, is not TO convex. TC convex sets are preserved under taking closure. And again, the connection to TO convexity, the interior of a TC convex is TO convex. So really, just to summarize, TC convex sets fulfill several of the nice desirable properties, and we still get, even if it might be ill-behaved to some extent, as I said, it can be disconnected, and we also can infer new insights for TO convex sets. However, also to give an interior description, so remember for TO convex sets, I started by saying, well, I want to take convex combinations in some sense. Well, then we had to do to see how to deal with cancellation. For this, we used this blown up operation for balanced entries, or equivalently the hyper operation. Here we have to use I'd say, more complicated workaround, namely what we call left sum, which a priori handles the cancellation by preferring the first summand in the sum. So in particular, let's look at this here. If we take the sum of -2 and 2, then -2 wins, and if you take the sum of 2 and -2, then 2 wins. So it's not commutative anymore, and so it behaves a bit weirdly. But actually, this is in some sense a known operation, because if we restrict to the -0, 0, -infinity vectors, then this left sum is just the composition of sign vectors or sign sets from the theory of oriented matroids, and this actually then also leads to the fact that we can study quantitative versions of oriented matroids with TC convexity. Yes, and so, but actually, even just taking combinations with this left sum is not enough. So let me just skip this motivation and get right to the definition here. So this is essentially what one would like to have. So we just take these non-negative combinations where we use the left sum as operation, but then also we have to require a cancellation property, namely, and now we can look at this here. If we take 2 points which differ only in the sign of one component, then this elimination property causes really a whole segment to appear. And with this left sum and these ideas, we actually get a very similar description of what we had before in terms of more classical convex combinations. But again, we need a bit more formalism. And if some of you would see a simplification, we would be happy. We haven't seen another way of describing these sets. Essentially, we have to go through all sign patterns which can arise for points. So that's why I have to look at hypercubes. So if we have some points in our convex set, then we have to first go via all the permutations of these points, as I said, because this left sum is not commutative. And then while all these points only differ essentially in their sign pattern, that's why we get vertices of such a hypercube here. And so the idea is, if we would have these 2 vertices, then suddenly this whole face would appear in the convex and the TC convex hull. And okay, so if you didn't get the details of these operators, don't worry. So the whole idea is, in a 3-step process, we arrive at an operator which really gives me, for a set of points, some subset of some, let's call it a hypercube, which is, as I said, this union of these faces. And now with this operator, we can actually write down something which looks like we would just take convex combinations. Namely, again, we just take non-negative scalars which sum up to tropical 1, and then we plug it into this operator. And with this, we get a characterization of the form a set is TC convex if and only if it contains all these combinations for all pairs of points, which is in some sense analogous to the requirement that the set contains all line segments between these points. And now for yeah, and yeah, just a different version of what we had in the beginning, where we required this here. Is then so now we cannot just take convex combinations, but we really have to use this phases operator to describe the convex hull. So how many minutes do I still have? Because yes, from now on I'm flexible. I was not sure when I started.
You certainly have 5 minutes.
Okay.
So if you try to wrap it up in 5 minutes, will be great.
Yes, exactly. Nice. Yes. So as I said, so from now on I'm quite flexible. So I wanted to give you this overview of TC convex sets and their representations. Again, so the representation of these TC convex sets gets quite technical quite quickly. Let me skip the part about TC hemispaces. This is a tool. Let me mention. So we really use a characterization of unsigned tropical hemispaces. Maybe this is just a pointer for you, Sergey. So we really relied on these insights about on unsigned tropical hemispaces for our structure theorem. Yes, and so on. And to get our separation results and all these representations. And let me just mention another application for those of you who like oriented matroids. So there's a notion of a, let's go to this slide. There's a notion of a so-called real Bergman fan, which is, let's say, like for a matroid, one can associate a Bergman fan as a geometric object. Then for an oriented matroid, one can associate a real Bergman fan, which is then dual to the signed matroid polytope. And this was mainly studied by Marcel Zelaya. And actually, as I said, observing that this left sum is essentially the composition, quantitative version of composition of oriented matroids. Sorry, we can write down a similar structure theorem as maybe. Sorry, I forgot in which talk. I mean, essentially I asked about this trop mu in the talk before, how you would define it, because well, this is the tropical convex hull of the evaluated circuits or co-circuits, depending on how you define it, and we essentially get a result in the signed case, just as a pointer for those who like oriented matroids and Bergman fans. Yes, and with this, I want to wrap up. I tried to give you an overview of the features of signed tropical convexity and why you should be interested in it. I skipped over the technical tools of TC hemispaces. Maybe those of you who like tropical hemispaces should take a look at that. I think this framework of signed tropical convexity has quite some potential to get new insights about tropical linear programming or its extension, signed tropical linear programming. And I'm intrigued about the connection with real Bergman fans and the whole hyperfield business, which is also happening there. And purely on the signed tropical convexity, and there are many open questions. Really, our proofs are really technical. It's very hard to get something explicit. We had to go through a lot of machinery of these hemispaces and abstract convexities to get these representations, and we would be happy to get more direct results here. So the whole theory only becomes nice if one goes to the more special class of oriented matroids or their quantitative extensions. And we also profited from signed tropicalization. I just mentioned this briefly, but I think the whole framework of signed tropical convexity can also help to understand the bigger questions about signed tropicalization of more general semi-algebraic sets. Thank you.
Questions? Anything from the audience, from Zoom?
Yeah, I have a question. When you define the TC convex hull of the points is the intersection of these positive closed half spaces. I was wondering if we need to take the signed valuation of the half space or not, because I think the definition on the slide was without, yes, here. Do we need the signed valuation of this half space? Because this
this half space is really only already a tropical Uppsala. Sorry, I'm still new with GoodNotes. So this half space is really a tropical signed tropical half space.
That is already tropically signed. Okay. Okay, thanks.
So what is known about separation in these versions of convexity?
Yes, so we have various versions of separation. We have we started with separation by TC hemispaces. You can separation with TC hemispaces works well, for all TC convex sets, but and for let's say finitely generated, so kind of TC convex polytopes, we can also separate by closed half spaces, not only by TC hemispaces. But we do not have a result about the general TC convex sets. We do not know separation results for them. So we have these two classes. Let's say we could show from the separation over Puiseux series a separation result with TC hemispaces. Yes, but they are, as I said, very non-constructive in the sense of Fourier-Motzkin elimination. So while classically one can do some projection constructions usually, or Fourier-Motzkin elimination, and all these things are quite constructive, we had to go via quite some tools to show existence of these things.
Okay, thank you. Any other question? If there are no questions, let's thank the speaker again.
Yeah, thanks again. Thanks for organizing the conference. I unfortunately have to leave, so if you have any questions or are interested in this, feel free to send me an email, and I wish you all a very nice evening, hopefully a nice evening still, and see you hopefully soon in real life.